Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering. And this is a review module where I talk about sinusoids and representing sinusoids using phasors and complex numbers. And so just to start off with, here's a picture of a sinusoid and the function that we use to represent a sinusoid. And sinusoids are without a doubt one of the most important functions that we work with in electrical engineering. And there's a couple of reasons for that. I mean, one reason is when we generate electrical power using a generator that is being turned by a steam turbine or a windmill or something like that, we end up getting a voltage that varies in a sinusoidal manner. But also we use sinusoids a lot because we can decompose things like audio signals or wireless signals into a sum of sinusoids using Fourier series and Fourier theory. And so we do a lot of work with sinusoids, and we have a lot of different ways to represent them. And this is probably, what I've got on this paper so far is probably the two most familiar ways to represent them. First of all, it's just a plain old picture, and second of all is the cosine function. Okay, so now let's just review some of the common parameters of the sine wave. First of all, we have the amplitude, which we represent by capital A. And capital A just represents the maximum value the sinusoid can take on in the positive and the negative directions. So it varies between A and minus A. The next parameter is the frequency. And when we express frequency as omega, it's typically in radians per second. And then the third parameter is time, t. And time, of course, is the x-axis on our sinusoidal plot. And finally, we have phase. And phase is just the shift of the sinusoid left or right. And so, exactly, of the sinusoid. And so if this phase was 0, then the maximum would occur, or if this phase was 0 and time was 0, then the cosine wave would be at its maximum. And so this amount, this shift, is a result of the phase shift. And of course, one of the fundamental properties of a sinusoid is that it repeats itself. And this is the time it takes for a sinusoid to repeat itself is known as the period of the sinusoid. And so we represent the period by capital T. And basically, when we're thinking about passing an argument into this cosine function, this cosine function takes an argument of radians. And so in order to repeat, or this cosine wave will, or this cosine function will repeat itself every 2 pi radians. And so in order for the cosine wave to go through a full cycle, the product of omega t has to be equal to 2 pi. Or in other words, the period is equal to 2 pi divided by the radian frequency omega. And, again, the units are radians per second. And frequency can also be expressed in terms of hertz. And usually we represent the frequency in hertz with a lowercase f. And frequency in hertz is just equal to exactly 1 over the period without this 2 pi argument. And finally, if we want to relate frequency in radians per second to frequency in hertz, omega is equal to 2 pi f. So one of the ways that we will be representing sinusoids is using something called a phasor. And a phasor is just a number, a complex number as it turns out, that represents specifically the amplitude and phase of a sinusoid. And so of course that's the amplitude and the phase right there. And so why do we represent amplitude and phase and forget about frequency? Well, frequency is often important as well, but in many of our circuit analysis problems, the frequency of the sinusoids will be the same throughout the circuit. However, we will introduce a number of elements, inductors and capacitors, for example, and resistors, that can potentially change the amplitude and or the phase of our sinusoid. And so we basically, just to sort of simplify this analysis, focus on those two parameters that are going to be changing. And as I mentioned, phasors are typically represented using complex numbers, and a complex number can be represented in many ways. So if we have a complex number z, we can express it as x plus jy, where x we call the real component of the number, and y we call the imaginary component of the number. And we sort of indicate that this is the imaginary component by multiplying it by the special letter j. And j is equal to the square root of -1. Now, often in many scientific computing packages, they will use the number I instead of j. But as engineers, we like to use j because I is typically what we use to represent current. So scientists, mathematicians and stuff will often use I, but we like to use j. And another way to represent a complex number, and this is maybe something that you would have seen in your first year circuits course, we represent it, the complex number, as having an amplitude A and a phase phi. And we can relate the real and imaginary component to the amplitude and phase, because amplitude is just equal to the square root of x squared plus y squared. And phase phi is equal to the inverse tangent of the imaginary component divided by the real component. And these are probably the two complex number representations that are the most familiar for you. But there is a third representation using something called a complex exponential. And a complex exponential is written as e to the plus or minus j alpha. And j again is equal to the square root of -1. And there's an identity that says this complex exponential is equal to cos of alpha plus or minus j of sine of alpha. And this plus or minus corresponds to the plus minus here. So if this is plus, that's plus. If this is minus, that's minus. And so we have a real component and an imaginary component, just like we have in our standard real and imaginary notation up above. Okay, so this notion of the complex exponential gives us a third representation for complex numbers. Excuse me. So we can write a complex number z as having, a real and an imaginary component, right? So the real component multiplied or added to j times y. We can use this angle phi notation. And we can also say this complex number can be represented by the amplitude A multiplied by e to the j phi. So we put the phase angle phi up into this exponent. And how does this work? Like, how can we write a complex number using this complex exponential? Well, remember that the whole idea of phasors is to represent a complex number basically as a vector, where we have a real axis and an imaginary axis, and then we draw our phasor as an arrow with a length a and an angle equal to the phase angle phi. And this phasor has a real and an imaginary component. The real component is x, the imaginary component is y. And how do we calculate the real and imaginary component? Well, of course, x is just equal to a times the cos of phi, and y is equal to a times the sine of phi. And so let's take another look at our complex exponential identity. So we have said that z is equal to the amplitude a times e to the j phi. And so what I'm going to do is I'm going to plug in the cosine sine complex exponential identity for e to the j phi. So we know that this is equal to a times the cosine of phi plus j times the sine of phi. And if we bring a into the brackets, we have a cos phi plus j times a sine of phi. And of course, this is just equal to the real component x. This is just equal to the imaginary component y. And so we recover x plus jy. And so this is why, I definitely do think that it's useful to have a complex number representation where we're dealing with the amplitude and the phase. But I don't like this notation because this is just a kind of a shorthand. Mathematically, this is not equal to this. However, if we use the complex exponential, as we can see here, a e to the j phi is mathematically equal to x plus jy. And so for the rest of my video lectures and any assignments and anything like that, if we want to represent a complex number in terms of its magnitude and phase, I will always be using this notation, and I will never be using that notation. So when working with phasors, and I guess complex numbers in general, we often want to do mathematical operations on them. And whether we're doing addition, subtraction, multiplication, division, there's certain representations that are easier for some mathematical operations and other representations that are easier for others. So for example, when doing addition and subtraction, the x plus jy notation is actually a little bit more convenient to work with. And so specifically, if we're adding two phasors together, z1 plus z2, this is x1 plus jy1 plus x2 plus jy2. You just add the real components together and the imaginary components together. So the result is x1 plus x2. That's the real component of the sum. And the imaginary component of the sum is y1 plus y2. All right. Next we have subtraction. Very similar. z1 minus z2 ends up being equal to the real component of z1 minus the real component of z2. So x1 minus x2 plus j times the imaginary component of 1 minus the imaginary component of 2, so y1 minus y2. For multiplication, multiplication is easier if we use the complex exponential notation. So z1 times z2 is equal to a1 e to the j phi 1 times a2 e to the j phi 2. And the result is just you multiply the two magnitudes together and you add the two phases. A1, A2, e to the j phi 1 plus phi 2. And that's just based on, the rule of exponents when you multiply two things together that have an exponent. The reciprocal of something is also easier to handle using the complex exponential notation. So 1 over z is equal to 1 over a e to the minus j phi. So you just invert the magnitude and take the negative of the phase. And we can extend this, we can combine the reciprocal result with the multiplication result to represent division. Z1 divided by Z2 is just equal to Z1 times the reciprocal of Z2. So we have A1 e to the j phi 1 times 1 over A2 e to the j minus phi 2. And then we just use the multiplication rule. So we multiply A1 by 1 over A2. And so our magnitude is A1 over A2. And then we just add the exponents together. And we get e to the j phi 1 minus phi 2. So that's division. Divide the magnitudes, or the magnitude of the first by the magnitude of the second, and then take the difference of the phases. And finally, I'm running out of room, but I'll just put it over here. Complex conjugate. If you take the complex conjugate of something, I usually represent it by a superscript asterisk. The complex conjugate, when dealing with this rectangular notation, is if we want to take the complex conjugate of x plus jy, we just take the negative of the imaginary component. So the real component is the same. Whoops. But we just have minus jy. Or if we want to represent this as using the complex exponential notation, the magnitude is unchanged, but we take the negative of the phase angle. Okay, so now what I want to do is I want to take the notion of phasors and complex numbers and review how we can use them to analyze what happens when we use sinusoids to drive a circuit that consists of resistors, inductors, and capacitors. And so let's start first with the resistor. And with Ohm's law. So voltage is equal to resistance times current. And if we understand this current as being sinusoidal, we can also represent this as R times a current with an amplitude of Im cos omega t plus phi. Now, this means, of course, since resistance is just a real number, that when we multiply R by this cosine, it's just going to scale this magnitude. And so both the voltage and the current are going to be sinusoids with a magnitude and a phase. And so we can represent the voltage and the current using phasors, and I'll write them using the complex exponential notation. So we've got some voltage with some amplitude Vm, e to the j phi. So the phase angle of the voltage and the current are going to be the same because R is just a real number and it doesn't affect the phase. It only affects the amplitude. So our voltage phasor is equal to resistance times our current phasor. And as a note, or sort of as a bit of shorthand notation, sometimes when I'm representing a phasor, I will write them as a kind of a bolded number. And so this voltage, I'm just going to represent like that. And this current, I'm just going to represent, or I'm just going to write like that. So we've got V is equal to R times I. And with this notation, we understand that voltage and current are both phasors. And so let's move on to the inductor. So we know that for an inductor, voltage is equal to inductance times the derivative of current. And if we substitute our cosine equation in and we take the derivative of it, we have inductance times negative omega Im sine omega t plus phi. And this is just the derivative of this cosine term. And so just, if that's not quite clear, just pause the video and Google that. Now we can take advantage of an identity here. Since we know that negative sine with an argument of alpha is equal to a positive cosine with an argument of alpha plus a phase shift of pi over 2, we can write our voltage as, I'll just sort of put this in a box. And then if we continue with our voltage equation, voltage is equal to L times omega Im. The negative sign disappears because I'm now going to write this as cosine omega t plus phi plus pi over 2. So we can see basically what happens when we pass our current through an inductor. It does this derivative operation, and this derivative operation does two things. First of all, it scales the magnitude of our current. Before, the magnitude of our current was Im. Now it's Im times the oscillation frequency omega. And it's also added a phase shift of pi over 2. If we want to write this in phasor form, we would say that the voltage phasor is equal to omega L Im, so this is our magnitude, e to the j phi plus pi over 2. Right? Because now our phase shift is not just pi like it was up here, it's pi plus pi over 2. However, a phase shift of pi over 2 can just be written as being equivalent to multiplying this whole thing by the imaginary number term j. So remember, j is equal to the square root of minus 1. And so what do I mean by this? So to be specific, a pi over 2 phase shift can be written as e to the j pi over 2 using our complex exponential identity. This is equal to the cosine of pi over 2 plus j of sine pi over 2. Of course, the cosine of pi over 2 is 0, and so this term is 0. The sine of pi over 2 is 1, and so this is just equal to j. And so let's revisit our inductor voltage. V is equal to omega L Im e to the j phi multiplied by e to the j pi over 2. Right? If we've got the summation of our exponents, we can just separate them out into two terms. I'm going to take this, I'm going to put it out front, and I'm going to write this as j, just like we've shown up here. And so this is equal to j omega L Im e to the j phi. Right? And so now we're back to our original current phasor, right, with an amplitude of Im and a phase shift of phi. And so to wrap this up, the voltage across our inductor is equal to j omega L times the current. And as we're going to see, this we understand this as the complex impedance of that inductor. Okay, and finally for the capacitor, we know that the current through a capacitor is equal to the derivative of the voltage. So this is just equal to capacitance times d of dt of Vm cos omega t plus phi. And so this is exactly the same thing that we had with the inductor, except we were taking the derivative of the current. And so I'm not going to show all these steps again, but using the same steps as we used for the inductor on the previous page, we can write the phasor of the current as being equal to j omega c times the phasor of the voltage. And so if we want to express, so the other two circuit components, the resistor and the capacitor, or sorry, the resistor and the inductor, we wrote in terms of voltage being equal to something. And so if we want to just express this in terms of voltage, we can write voltage is equal to 1 over j omega c times the current, to put it in the same form as the other equations. And so is this okay? Are we breaking any rules by taking the reciprocal of this? Not at all, right? Because this j omega c is just a complex number. So j omega c is just a complex number with magnitude omega c and a phase shift of pi over 2. And so 1 over j omega c is just equal to a complex number with a magnitude of 1 over omega c e to the j minus pi over 2. And so that is important to realize, right? This j omega c term is just a complex number with a magnitude and a phase, so we can take the reciprocal of it just like we would any other complex number. And so finally, we can use these relationships to define what we refer to as the impedance of the resistor, inductor, and capacitor. And impedance is, in general, a complex number. We represent it by the phasor Z. And again, a phasor is just a complex number. So the complex impedance is just equal to the phasor of the voltage divided by the phasor of the current, right? So it's sort of a version of Ohm's law. You can think of it as a complex version of Ohm's law. And so let's take a look at our resistor component first. So we have our complex phasor voltage across our component, our phasor current going through the component, and we've seen already that voltage is equal to, I guess we wrote it the other way around. Voltage is equal to resistance times current. And so the impedance of a resistance, if we just take V divided by I, is just equal to R. So the complex impedance of a resistor actually isn't complex, it's just the real number R. We can do the same thing for the inductor. Voltage across the inductor, current flowing into the inductor. We saw, or we've just seen that voltage is equal to J omega L times the current. And so if we take the ratio of voltage divided by current, we get the complex impedance of the inductor, which is just equal to J omega L, right? And remember, this J omega L is just a complex number. Its magnitude is equal to omega L, and its phase is equal to pi over 2. Finally, if we take a look at the capacitor, voltage across the capacitor, current flowing into the capacitor, voltage is just equal to 1 over J omega C times I. And so that means the complex impedance of a capacitor is equal to 1 over J omega C. Again, this is just a complex number. Its magnitude is 1 over omega C, and its phase is minus pi by 2. And so we can actually use these impedances to analyze circuits using techniques that are very similar to the techniques that we learned when we were just doing resistive circuit analysis with DC voltages and currents. In fact, they're basically identical, except we're working with complex numbers instead of real numbers. And just to show how this circuit analysis works, I'm going to analyze this following fairly simple RC circuit. We've got some voltage at the input. We're going to define our output voltage as the voltage across the capacitor. And the current flowing around this loop is going to be the phasor I. And we can use exactly the same techniques that we used for resistive circuit analysis. And so I'm going to use Kirchhoff's voltage law to say that the voltage applied to the circuit is equal to the voltage drop across the resistor plus the voltage drop across the capacitor. And the voltage drop across the resistor is equal to the current phasor times R. The voltage drop across the capacitor is equal to 1 over J omega C times the current. And we want to just express the output voltage in terms of we want to express, or we want to have an equation just in terms of the output and the input voltage. And so we want to get rid of this current equation, but we know that current through the capacitor is equal to J omega C times the output voltage. And so what I'm going to do is I'm going to take this equation, I'm going to substitute it in there, I'm going to substitute it in there, and we get J omega C times R times V out plus V out, right? Because 1 over J omega C cancels J omega C. And so if I just sort of group terms, I can express the output voltage as being equal to 1 over J omega C plus 1 times the input voltage, right? So that's just KVL, and we just used these impedances just like we would use sort of normal resistances, except that this is, of course, these are, of course, complex numbers. And we would just handle them inside our calculators using the complex number feature of our calculators. Another really nice thing about this complex impedance phasor analysis is that we can just completely forget about the fact that this component is a resistor and this component is a capacitor, and we can just draw them as black boxes with a certain complex impedance Z1 and another complex impedance Z2. And if we want to determine the output voltage, we can just treat these two impedances again just as we would resistor values. And so we can determine V out just using the voltage divider equation. So V out is just equal to the impedance Z2 divided by the summation of Z1 plus Z2 multiplied by the input. And at this point, we can actually really use any two components we want. We could have a resistor there, we could have an inductor there, really whatever. But if we want to be consistent with the circuit we had on the previous page, Z2 was equal to a capacitor, so its complex impedance is 1 over j omega c. Z1 is a resistor, Z2 is a capacitor, 1 over j omega c. Times the input. And if we multiply by j omega c at the top and bottom, we get 1 over j omega RC plus 1 times the input voltage is equal to the output voltage, which is exactly the same expression that we had in our previous for our previous analysis. And just one last sort of point. One of the reasons why I'm reintroducing the this sort of phasor analysis or impedance analysis for AC circuits is because in our Circuits 2 class, we're going to be interested in how these circuits respond when we change the frequency of our sinusoids, omega. And this is not something you would have seen in your first year circuits class. So in first year, generally we assume that omega is fixed because perhaps we're analyzing, like an AC power circuit where omega is equal to 60 hertz, and this is just sort of the power that we have in our electrical grid, for example. So the frequency doesn't change. However, in our class, when we look at filters, we want to design circuits that behave differently for different values of omega. For example, we may want to design a circuit or a filter that will allow a certain range of frequencies to pass through, but will block another range of frequencies. And we'll get into this in a lot more detail later on. I just want to now kind of explore the behavior of this particular circuit when we have, let's say, a very low value of omega or a very large value of omega. So let's start with a very low value. So let's assume that omega is equal to 0. In this case, our output voltage, VO, is equal to 1 over j omega, 1 over j, where omega is equal to 0 times RC plus 1. So of course, this is equal to 0, so we have 1 over 0 plus 1, or 1. So for omega equal to 0 and for very low frequencies, I'm getting ahead of myself here. So this is times V in. So this is equal to 1 over 0 plus 1 times V in, or in other words, it's just equal to V in. So basically for omega equal to 0 and for omega equal to very low frequencies, our output voltage is just equal to our input voltage. So our circuit basically allows low frequency signals to pass through more or less unchanged. However, let's take a look at what happens when we have a very high frequency signal. So omega equal to infinity. Our output voltage is equal to 1 over j times infinity, RC plus 1 times our input. So 1 over infinity times our input. In other words, equal to 0. So for very large values of frequency, our denominator gets so big that the output of our circuit basically goes to 0. So we seem to have designed a circuit that will allow low frequency signals to pass through more or less unchanged, but will block high frequency signals. And as we're going to see later on in class, this is what we're going to refer to as a low pass filter. And we'll talk about what low pass filters are used for. But just to continue on with this kind of line of discussion, let's introduce one more circuit. So for our final circuit, we have an input voltage, output voltage, and we've swapped the location of our resistor and our capacitor. And using this kind of philosophy up here, we can still have this exact same voltage divider equation in terms of these generic complex impedances. However, in this case, Z2 is going to be equal to R, and Z1 is going to be 1 over j omega c. 1 over j omega c. So our output voltage is going to be equal to j omega RC over j omega RC plus 1 times the input. And if I can just fit this in on the bottom of our page here, let's take a similar sort of look at our circuit. Let's assume that we have omega equal to 0. In this case, our output voltage, if we substitute in 0 here, we're going to, or if we substitute in 0 for omega, we're going to have 0 over 0 plus 1 times our input voltage, or in other words, we're going to get 0. And so we now have a circuit that will basically block the input voltage for omega equal to 0, or very low frequencies, because we have an omega term on our numerator now. And for very high frequencies, omega equal to infinity, our output voltage is equal to infinity over infinity plus 1 times our input voltage, which is approximately equal to infinity over infinity times our input voltage, which is equal to 1 times our input voltage. So in other words, for very high frequency terms, the numerator is roughly equal to the denominator, and the output is equal to the input. And so we've now designed a circuit just by swapping the location of the resistor and capacitor that has exactly this opposite behavior to our earlier circuit. So up here we had a circuit that passes low frequency signals but blocks ones where omega is large. And now we've got a circuit that blocks signals where omega is low and passes signals when omega is large. And this is what we're going to refer to as a high pass filter. So again, we're going to look at this concept of filtering and frequency selective circuits in a lot more detail, but it is tightly and very related to the techniques of analyzing circuits with complex impedances. So that's why I wanted to at least introduce the notation, or introduce the concept here.